Welcome. Today we're diving into Laplace transforms, a powerful tool in solving differential equations. I'm Dr. J. Sivarangini, and together we'll explore how transform techniques simplify complex problems, especially in partial differential equations. Let's get started and see how these methods open new doors in mathematics. Let's start by grounding ourselves in the essentials. We'll cover the core definitions that form the backbone of the Laplace transform. Then we'll explore its fundamental properties, the rules that make it work. After that, we'll look at the key operational theorems, which help us manipulate and apply the transform. Finally, we'll review some standard solutions to common problems, setting the stage for deeper understanding. This framework will guide us through the rest of the talk. Let's start with the basics, what the Laplace transform actually is. It's a linear operator, which means it takes linear differential equations and turns them into algebraic equations. This makes solving them a lot simpler. Essentially, it transforms functions from the continuous time domain into the complex frequency domain. We use the symbol L to represent this transform operator. As long as the integral exists, the Laplace transform applies to functions defined for all positive real values of time. Let's explore two fundamental properties of transforms that make them so powerful. First is linearity. This means the transform of a sum of functions equals the sum of their individual transforms. It lets us break down complex problems into simpler parts. Second, the constant multiple property tells us that if we multiply a function by a constant, we can factor that constant out of the transform. Together, these properties give us flexibility and control when working with transforms. Let's explore how Laplace transforms handle derivatives. Instead of working directly with time-based differentiation, the transform turns it into multiplication by a variable, usually s for the first derivative. This means multiplying by s once. For the second derivative, it's like multiplying by s twice, or s squared. More generally, for the nth derivative, the transform involves multiplying by s to the power of n. This shift makes solving differential equations much simpler. Here we have a table of standard Laplace transform formulae, a handy reference for solving differential equations. Each formula shows how a common function in time translates into the s-domain. For example, the transform of sine and cosine functions, exponential growth, powers of t, and even the constant function. These building blocks let us break down complex problems into manageable parts. Knowing these transforms by heart speeds up the process and deepens our understanding of system behavior. Now we're diving into exponential transforms, a key concept that helps us understand how certain functions behave when scaled or shifted exponentially. This slide guides us through the proof process step by step. We start by stating what's given, then work through the logical steps to prove the relationship. It's about connecting the dots, showing why the transform holds true under these conditions. This foundation is crucial for everything that follows. Now, let's dive into the derivatives of hyperbolic functions. We'll start with hyperbolic sine. Using its definition, we can find its derivative step by step. Then, we'll do the same for hyperbolic cosine. Understanding these derivatives through their definitions helps us see where these formulas come from, not just memorize them. It's a solid foundation for working with hyperbolic functions in calculus. Now we're diving into trigonometric transforms, specifically the sine and cosine transforms. Here, we'll walk through the proofs for both, showing how they're derived. The key tool we use is a standard integration formula, which helps us break down these transforms step by step. This foundation is crucial for understanding how these transforms work in practice and sets us up for applying them in different contexts. Let's dive into power functions and gamma integrals. When our exponent is a positive integer, things simplify nicely. We have a straightforward case to work with. But the real power comes from the general formula involving the gamma function, which extends beyond just integers. We'll also walk through how to derive this using integral substitution, connecting the dots between these concepts. This sets the stage for understanding more complex integrals and their applications. Now, let's dive into some special and fractional power cases. These come up when we're working with exponents that aren't whole numbers, like negative halves or fractions. We'll see how these transform functions in different ways. For example, quadratic, linear, and constant forms all behave uniquely under these powers. Understanding these cases helps us handle a wider range of problems, especially when things don't fit into neat, whole number exponents. It's a key step in mastering more complex functions. Now, let's look at solving problems involving higher powers. We'll use a specific identity to simplify these expressions. First, we apply the identity to rewrite the problem in a more manageable form. Then, we evaluate the result step by step. This approach helps us handle powers that might otherwise seem complicated, breaking them down into something much easier to work with. It's all about recognizing patterns and using the right tools to make the math straightforward. Let's break down the core engineering domains that shape how we analyze and design complex systems. First, signal processing uses the Laplace transform to turn time-based convolutions into simple algebraic multiplications, making filter design much more manageable. Mechanical dynamics models how structures respond to forces, whether sudden impacts or steady vibrations. Control systems focus on transfer functions and pole zero plots to ensure stability and predict system behavior. Finally, electrical circuits leverage S-domain impedances to simplify transient and steady-state analysis. Together, these domains form the backbone of modern engineering design. Thank you for joining us today. We appreciate your time and attention as we